Good afternoon, everybody, and I would like to thank the organizers for giving me invited talk. This is an honor for me, and it has been always my wish to attend one of these PolyTrib because it started quite long ago and became very popular among polymer tribologists because this is the first in the world to focus on just polymer tribology. You might know that myself and Professor Briscoe, we had edited one book on polymer tribology long back, but nothing of this sort, conferences. So it's very good development, and as somebody said, that let's hope that we will continue this. So today in this talk, I will focus on some aspects of polymer composites and trying to find out some rules about how we can design a good polymer composite for tribological applications. Because tribology many times has got a lot to depend on the bulk properties, but there are a lot of things which actually doesn't depend on bulk property, and that's why this becomes much more complex and very interesting. So first of all, let's see these few statements. So pure polymers, they are good for bulk properties but do not have much tribological applications with few exceptions. So there are some exceptions, but most of the polymers you will find that tribologically they are not good by themselves. So they must be modified. So this is very, very important. They must be modified with some fillers. And normally we go for changing the bulk rather than coating. But of course coating is also one option for polymers. And for polymers we generally don't go for lubrication. But of course lubrication is also one option we have. Tribological applications include, as we have been discussing here, bush bearings, cages for bearings, gears, artificial joints, brake application, and there are many applications. So tribology, polymers have got a good place in tribology, and there are a lot of applications, and there are a lot of applications where only polymers can do the job. For example, space application where polymers are more important, water lubrication case, for hip implant joints. These are the applications where you cannot replace polymer with some other material. So that way they have a niche. So for example, this one ball bearing cage, and another example is plain bearing of PEEK composite. So I just took this picture from late Professor Frederick's paper. As you know, Klaus Frederick contributed hugely to this field. So there are lots and lots of papers and books written by Professor Frederick. So this is one, in one of his paper he has given this one. So basically he has given this pyramid of different polymers, pure polymers, starting with the commodity polymers, which are much cheaper, but still they have some good properties we can exploit. As you go up, then you have got these engineering polymers, UHMWP, PMMA, polycarbonate, and further on there are some thermosets, and as we go to the top of the pyramid, they are very highly specialized polymers. Often they have very good thermal property, so often they are appreciated for their thermal property. They have good mechanical strength, mechanical properties, so in combination they can make a good material for tribology. For polymers, you might have seen this Greenwood-Williamson plasticity index, and here the ratio E over H for metals and ceramics are in the order of hundreds, whereas for polymers it is in the order of 10. So what does it mean is that for polymers can deform plastically much easily, compared to metals and ceramics. Polymers are very prone to plastic deformation, and they are greatly affected by temperature and shear rate. So this is another important thing to note. Obviously, temperature has very great effect, but also shear rate, how fast we are deforming the material. So that's why you see there are a lot of speed dependence on tribological performance. And another thing is glass transition temperature. For polymers, it is very close to room temperature, and often they change quite drastically. So glass transition temperature also is very, very important, because this will determine whether the polymer is going to fail by brittle fracture or plastic deformation. So these are the important basics about polymers that we have to know. Now talking about friction, the two-term model of friction is generally applicable. It is applicable for metals also and for polymers too. And where mu is given in two terms, first is the interfacial terms and the second is the plowing component. So these roughly these are the two main components. Of course there are other effects also happening in the friction, but these two will include all the effects. So interfacial means right at the surface, the shearing action, the shearing that is happening, and so it can be, for example, lubricant, but often it is a thin layer that is formed at the top surface, and it's the property, the shear property of this thin layer, which is contributing to the interfacial friction, and it is given by the friction because of adhesion. This is also known as adhesion or adhesive friction, divided by the L, which is the load, and which is then given by this equation. Tau is often written in the terms of tau naught plus alpha P, where P is the pressure. So this modifies in this way. And the second term is plowing term. Plowing is basically not just the interface, but deep into the material. So that means the mechanical property might be very important for plowing, but theoretically plowing is given by this equation. The plowing coefficient of friction is given by this equation, where theta is basically the angle of attack, how sharp the asperity is. If we consider this as asperity, what is the sharpness of the asperity? That is defined by theta. In the case of polymers, as well as in the case of metals, but for polymers, this is very, very important, that we have to use the JKR model instead of the Hurgen equation. And the difference is that in JKR model, we have got this work of adhesion. Work of adhesion is included in the equation for contact area. So if we are going to calculate contact area, and contact area is very, very important for us to calculate, so the work of adhesion is very, very important. So here we can see the relation between work of adhesion and friction. In fact, long back in 1995, Rabinowitz had given this graph in his book, where he has plotted the work of adhesion divided by hardness, this ratio, as a function of coefficient of friction for metals. So in those days, mostly he was working on metals. So what this says is that the coefficient of friction is low if this ratio is low. So that means a material should have low work of adhesion and it should have high hardness. This combination has to be there. So if you have this combination, then you end up with low coefficient of friction here. In our work, we have also related friction to adhesion. And in this case, what we have done is we have used Bradley's equation for the attractive force between two materials. So it is possible to actually, using the surface energy concept, it is possible to calculate the attractive force using this equation. And we actually used empirical method to derive this equation, where we can relate coefficient of friction coefficient of friction, here we say initial coefficient of friction because before the wear takes place. So the initial coefficient of friction is an exponential function of the force, attractive force that is acting. So that means the friction is directly related to adhesion, means by this exponential equation. So there is ample evidence that friction is related to adhesion in addition to many other factors. So that's about friction. What about wear? Actually, it is very hard for polymers it is very hard to give any kind of model that can take care of the wear part. But this graph, you will see, it has come out from Ratner and others' work, where specific wear rate was related to 1 over sigma Fe, where sigma F is the tensile fracture stress and E is the elongation at fracture. So in some way it is related to the plastic deformation property of the material. Okay. So if we plot this at least for pure polymers, we can see some sort of relation, a linear relation. However, there are many other equations which has been also given, and in some way hardness also has been related. But here hardness is not the only factor. Coefficient of friction, the ability of the material to deform before fracture, these are also very, very important. So again, specific wear rate is a very, very complex when it comes to polymers. So we can try to ask question, is Archer's law valid for polymers? So for metals we often use that Archer's law, but actually for polymers, if you see, it's not related, because for example here we have got two cases, UHMWP which has got lower hardness, PMMA has very high hardness, but if you look at wear rate, they are contrast. So there is an opposite relation. So perhaps Archer's law is not valid for polymers, because there are many other things, adhesion, strength, percentage elongation and failure, which affect the wear of material. So basically what it shows is that the friction and wear for polymers is very, very complex, and therefore we have to resort to experimentation, lots of experimentation, and see the trend. So this graph summarizes from the literature values different pure polymers, these are not composites, and what are their specific wear rate. So normally you will see the specific wear rate is in the range of 10 to the power minus 6 to 10 to the power minus 4 for different PV values. Again, PV value is another important factor, and here these PV values are quite low. So if the specific wear rate for polymers is quite high for many of the engineering applications, then what can we do? So again, Frederick has given this picture to show what we can do for polymers, to make polymers or design polymers which can satisfy our job, basically coming to polymer composites. So where polymer matrix should be high temperature with high stability and easy processability for the cost. Some sort of internal lubricants should be there, solid lubricants or liquid lubricants. Then nanoparticles enhances thermal conductivity. For example, multi-wall CNT can enhance the thermal conductivity. Smoothing of the surface topography. Many times you will see that the nanoparticles are, what they are doing is they are actually polishing the counter surface, and that's why the wear will go down. And short or long fibers will enhance the creep resistance, strength, stiffness. So this is a combination of the whole recipe of how we can make polymer composites for many applications, for most of the engineering applications. So Frederick and his other co-workers gave this kind of what they call it spider map. Okay. So here you can see that for material which has got MW and multi-wall nanotubes, graphite and short carbon fiber in these proportions 3, 10, 10 weight percentage, it gives very good wear resistance, okay? But also gives very good electrical conductivity, by which also we can say that it has good thermal conductivity as well. So higher electrical conductivity, higher tensile and yield strength, even at the expense of fracture toughness, is good for wear resistance. So fracture toughness on this line is slightly lower, but all other properties are good, and it gives a very good wear resistance. Okay. So when we are looking for designing a polymer composite, perhaps we have to get this kind of ideas, get this kind of concept where we enhance the strength, but also we think about enhancing the thermal conductivity of the composite. In this one, they have shown that, for example, traditional fillers, which includes short fibers or long fibers, whereas compared to nano fillers, where we have nano TiO2, actually nano fillers tend to give better result. And one of the reason is they can make the material more thermally conducting, and another is they have polishing effect on the counterface. In the next part, I will show you some of the composites that we made, and we have tested them for various load and speed conditions. So we made 3 types of polymer composites. All were epoxy based. So epoxy based basically because it's thermoset. Normally it has got good thermal properties. So epoxy with hardeners, and the fillers were MOS2. Here it is volume percentage, that's why this number is a little bit strange. And UHMWP particles. So here we have used UHMWP as a solid lubricant. MOS2 also is a solid lubricant, but MOS2 has got some other effects also. It can harden the material, it can make the bulk better. Then some other ideas we have tried. For example, adding 2 weight volume percentage of Kevlar fiber in it. And another idea is where you can use liquid lubricant as a filler. So here the filler inside is liquid lubricant, so that gives us continuous supply of lubricant at the interface. So it is still dry, but with some amount of oiliness at the interface. So these 3 composites we have tested, and the tests were conducted on a block on cylinder tribometer, so something like this. Here there is a block and there is a cylinder here. So the cylinder is rotating and the ball is sitting on top of it. The contact area was calculated using the Hertzian contact. So since it is a line contact, so we use this equation for line contact. And then we calculated the pressure. So this is not nominal contact area, this is Hertzian contact area. So micro hardness, for example, the first one where we do not have Kevlar, so this is a MOS2 and UHMWP. So hardness is in this range, about 130 megapascal. With Kevlar, there is slight improvement, but with base oil, the hardness goes down. So, and some other properties, for example, thermal properties and TG. So, as I said, TG is also important for us to understand, but sometimes it may not have direct correlation. So, for example, in this case, for the base polymer composite, we have got in the range of 100 TG, but for the other composites with oil and with Kevlar, actually the TG is slightly lower. Okay? So that means it is behaving a little bit brittle nature. And also TGA, where we find out the thermal stability by adding the fiber or the oil inside, actually thermal stability has gone down. Okay? So, but not necessarily that they will be affecting tribology in the same way. So coefficient of friction for these three composites, the MS is the base composite, K is the Kevlar composite where we have added Kevlar, and B is the where we have added the base oil as additional components. So these are all hybrid composites. With load, as we increase the load, the coefficient of friction has gone down. And in terms of specific rate, also a specific rate has got some complex behavior. Initially it goes down, but later on it starts increasing. So this is a complex behavior in terms of friction and wear. They may not correlate with each other. It is possible. So what we did was we calculated the PV, okay? Because PV is a very good parameter to understand whether your material is actually capable of handling very high stress and high sliding speed. So here the PV comes out to be quite high, so 50 up to 50. Actually in the literature you cannot find polymer composites which have been tested for up to 50. And some of the composites like MS composite, which is the base composite, actually it failed at around 37, so it could not go further. But other composites like with Kevlar and with base oil, actually they survive even at very high PV factor. Okay? So coefficient of friction and also wear. Although you will see that the wear starts going up, okay? So obviously at some point it will accelerate. The wear rate will accelerate and it will fail very drastically. But still these composites with epoxy and these fillers, they have given us very high PV factor. And we measured the temperature, but the temperature was actually the disk temperature after the test. So you stop the test and immediately you take the surface temperature. And you can see that there is a drastic increase in the interfacial temperature around here, 37 PV, and which indicates why some of the one of the composite, which was MS, actually failed at this point, because the temperature simply starts going too high, and the failure is because of the thermal effect. So that this says that if we can increase the thermal conductivity of the material, then it is good in terms of tribology. It can survive much higher PV factor. And you can see these specimens how they fail. In some cases completely cracked. Okay. In another case, very gross plastic deformation or scuffing happened. So this is the complete failure of the specimen. Here also we saw the transfer film. So as we know that polymer composites and polymer in general, MS composite, the base composite forms transfer films. Here it is slightly thicker than for the Kevlar and for the with oil here. And on the surface of the composite we could see some cracks happening. So these are some of the cracks, whereas for the base oil where we added liquid oil, actually we did not see so much of cracks, but there are presence of oil on the surface. So we were thinking about how we can plot this, because there are so many factors that is affecting. So for our material selection, how can we design? So this can be a one map that we can practice. For example, specific wear rate times the coefficient of friction. So both we are trying to lower down. So if we multiply them, we want them as low as possible. Okay? And as a function of PV. We keep the PV because PV is a very good indicator of the performance. So if you are trying to make high performance polymer composites, it is better to compare their PV. Of course, comparing load and speeds are also important. And here from the literature, these are all literature values and these are our values. Actually, most of the time you will see that the literature is around here. So that means PV factor 5 or less than 5. And this is multiplied by coefficient of friction here. So this is in the range of 10 to the power minus 7 to 10 to the power minus 6. These are good polymer composites that have been made for tribological applications. So, but if you try pure polymers, obviously you will get somewhere here. So our goal is that we should have high PV and low product of specific wear rate and coefficient of friction. So somewhere here, if we can get somewhere here, then perhaps we can make a good polymer composites. So I think this exercise will continue. We will try to find some other combinations and also see what in the literature people have done. Okay, but somehow we have to try to get here for good engineering application of polymer composites. So I will conclude here. Polymer composites are excellent for use as materials for tribological components. So it's very good news that many new applications are coming, and many companies, especially here I can see a lot of companies are now involved in making polymer related tribological components. Hybrid composites consist of thermosetting polymers with strengthening fibers, solid lubricants, and thermal conductivity enhancer. So we have to have all these three. Okay? So we cannot just manage with one. We have to have all these three in order to make very good polymer composites. High PV factor. So this is PV factor. We must be focusing on very high PV factor for any tribological need. Another thing that is a big problem in this field is there is no standard. There is no standardization of the composition. So it's like I am making one recipe and somebody else making another recipe. So it's all over the place. So how can we bring them all into one thinking? So some sort of standardization is important so that we understand what exactly is for making good polymer composites for very demanding engineering applications. So perhaps some thinking on this we will have to do in the future, and we can perhaps one day we can find a standard material which can give us the best performance. Just like for metals, for example, I see we have a bearing steel. Okay, so all over the world people are using the same composition more or less. Similarly, in the polymer composites also, perhaps we can come down to some composition, some combination of composition, so that we can all use the similar kind of materials. But anyway, that will continue. So thank you very much for your attention.
Thank you for a very comprehensive and interesting presentation. I think there must be a lot of questions related to this presentation. Please, the floor is open.
Thank you. I just have a quick question. Actually, it's like to get more information from your expertise. Are you willing to test some polymers under electrified conditions?
Yeah, I haven't done that kind of work. So I think that people are trying to increase the electrical conductivity by adding things like graphite and carbon nanotube, and that is helping to improve the electrical property of the material. So yes, if you are working in an electrical environment, so the wear will go up because of the charging effect, and friction will also go up. So we have to try to make thermally conducting material, electrically conducting material, and the only way I would think is by adding graphite or carbon nanotube. Okay. But also some of the metal fillers can also be added, metal powder like copper or bronze can also be added to improve the electrical conductivity.
Okay, thank you so much.
I can yell, maybe. Okay.
Thank you, Professor Simla, very nice presentation. I'm very happy to see in the last but slide showing the tribology map of selection of material. Is what way is different from ASPE map?
Yeah.
Is it can be correlated with ASPE map and tribology map for the polymer applications?
Yeah, so ASPE's map for the bulk properties are all good, but when I see the tribological part, I find a little bit of problem, because ASPE has relied a lot on hardness, and again assuming that Archer's law is valid for, but actually Archer's law is not valid. If you see, it is not valid. So it's a combination. Hardness is important, but it's a combination of things, many properties. So that's why here it's basically based on the experimental results, so specific wear rate and coefficient of friction. So this parameter perhaps can be used for material selection along with PV.
Thank you.
Okay, Nazan here.
Thank you. I was just wondering, how do we do the final sentence of your conclusion, the standardization, when all the time comes new particles, new polymers, sort of how, I mean, if we can't do that, so what would be your suggestion? Because I don't think so we can get to that point with the polymers.
So I just feel that there is one reason why it happens.
Yeah.
It's because it's so easy to make different composites, right? I can make in the lab 5-10 types of different composites, and which we have been doing, all of us have been doing. So that way we never come to a conclusion. For example, as I said, Professor Frederick has worked so much in this field, but we have not come to a conclusion that, okay, this is the composition, this is the right thing, and this is everybody should do. So unfortunately, we may not come to one conclusion.
But that's maybe for polymers, we will never have that conclusion. That's maybe the advantage of it.
Yeah, this is this is the advantage, but then your advantage becomes a disadvantage, because then nobody is agreeing on anything, right? And companies are making, but they are also keeping their composition secret. I mean, they just change the recipe and they say, you know, we have different recipe. So this is what is happening. Whereas in the case of metal, not everybody can make tool steel or whatever steel. So it's very expensive to make. So this is one reason. So it's kind of advantage has become some sort of disadvantage. So we are working all over the place. We are not on one platform. But I think just want to add, so perhaps what is called round robin type of experiment, where some of the labs decide on some of the compositions, and then we send out the specimens to be tested in different labs in the world, and that might help. Yeah.
I saw on the specimens you had the full failure of the specimens.
Yeah.
I mean, that means you really let it go. So how long took to get to these failures? Because that's a full
I think they were all run for fixed 2 kilometers of distance. So
much,
yeah, but of course they must have failed before. So I don't remember right now exactly, but they were complete failures, so we did not proceed further.
So when I see this and the TGA data, I was wondering if you have done the degree of polymerization measurements when you mixed polyethylene and the stuff with the epoxy. Did you measure the degree of polymerization?
No, we have not measured on that one. So with epoxy, always degree of polymerization is very, very important, and that is affected by how much hardness you put in, how long you keep it at higher temperature, curing. So that variations are always
Could be a nice indicator for the TGA data as well.
Yeah.
Very nice presentation.
Yeah, for the future, yes, we will.
Thank you for your presentation. This is Takeshi Kunishima from JTEC Corporation in Japan. So actually, we are using the polymer sliding paths, especially under lubrication, especially grease lubrication. And in some cases, the Archer law is not appropriate because even, for example, the glass fiber reinforced composite is used. Of course, hardness is much higher, but the wear resistance is deteriorates. So it is not appropriate for Archer law. So do you have any idea, especially under lubrication, which wear law is appropriate to predict some tribological phenomenon?
Yeah, so with polymers, in most of the cases when we are conducting tests, this is in boundary condition or mixed lubrication.
Yeah.
We never go to hydrodynamic lubrication. So again, which means that there will be dry contact at the interface.
Especially boundary lubrication.
Yeah. So even with grease, we have tested the same polymer composite for grease also. So yeah, it's very difficult to say any kind of model. Although in our review papers we have shown several of the wear models people have given, but they are all applicable to certain particular conditions only. There's no generalized. So in general, we can only understand that these are the properties we have to care about, but all the details will go into what kind of composite you're making. So I don't have any answer for that.
Okay, thank you for your comments.
Okay, I'd like to ask finally, most of this material development is based on experimental trial and error, and of course thinking about what would be the right way. Do you think that modeling could be used as a tool in order to help in the development of different composites?
Yeah, so in tribology, I think there are a lot of limitations in terms of modeling. So for example, we have been trying MD simulation for like bio application, polymer application for bio. We have a lot of limitation how far we can model. So since computationally it's very challenging, and also so those are the things. So I think by modeling it's very hard. Bulk you can deal with it because bulk is a continuous phase, but the surface is not continuous. A lot of discontinuities, a lot of external effects are there, humidity, temperature. All the effects are there, and taking care of all the effects in your simulation is just impossible. So yes, we can understand how a particular thing will affect. Let's say how humidity is going to affect my material. That can be studied, but overall will be very hard. So we have to resort to experimentation. And that's one thing about tribology. It's a both good thing and bad thing. Right? So good thing that it keeps us busy, right? And bad thing that you can never come to a conclusion and never say, okay, this is the model and that I can use it for designing. It will not work.
Okay, thank you very much for